Hi everyone, so today we're going to start talking about different types of cell transport. So there are two types of cell transport, and just to give us a little bit of background knowledge, transport itself is going to be the movement of substances in and out of our cell. So again, that's going to involve our cell membrane. So there's two types. The first is passive. This is what we are going to focus on today, passive transport, and it requires no energy or no ATP for it to happen. And the second is active transport, and that requires some sort of energy or ATP. So passive transport, we have three different types: diffusion, osmosis, and facilitated transport or facilitated diffusion. And we'll get into details about all three of those as we go on today. But what I do want to go over first is what all three of these have in common. So all forms of passive transport have these things in common. Substances move from high to low, and I'm thinking of high to low as in concentration. So if we have a cell like this, and we only have 2 in here, and we have 15 dots out here, we're going to want to move from this high concentration to that low concentration. They all require no energy for these things to be done, and they rely on the motion of particles. So the particles themselves are moving in and out of the cells. That is a heavily big idea when we're talking about passive transport here. So let's talk about what a concentration gradient is. So a concentration gradient is the difference in the number of particles from one area to another. So if we take a look here, we have signs that look about even. So it's even on this side and it's even on this side. So at this point there is no gradient or concentration gradient. But if we say added a couple dots on this side, we're no longer even on both sides. And since there's more here, again, we're going to move to that high to low direction. We're going to move here. So there is a concentration gradient in this image because I've added more to our side here, and it's going to bring more of those solutes over to the other side to make balance again. So the first one that we're going to be speaking of for the types of passive transport is going to be diffusion. So diffusion is the process by which substances move from a higher concentration to a lower concentration to make a dynamic equilibrium. So we know that dynamic equilibrium means when things are equal on both sides, but this word dynamic means it's something about movement. So a dynamic equilibrium, our molecules are still moving, but there is no concentration gradient. So again, what that means, if we have two beakers here, or if we have one beaker in a cell, we're still going to have even amounts here, but we're still going to have movement in and out of the cell, no matter what's happening, just to keep that balance, to have that movement still occurring within our cells. And again, no energy, does not require energy to do diffusion. One more thing I'm going to add to our definitions here is with diffusion, it moves through the cell membrane itself. So diffusion, we're going straight through that cell membrane. So again, Diffusion can be used for cells, but it can be used for a lot of other things. This is a great example here. If we drop some sugar into the water, all those sugar molecules are going to be clumped, but then we're going to start to see them diffuse into the water, start moving from where there's a higher concentration to where there's a lower concentration, until we see that equilibrium being matched. Same thing here. We start with lots of high concentration here to low concentration, and we're going to see that movement slowly occur until we have that equilibrium. Same thing if there's multiple solutes, both of them are going to want to equal out on both sides. So we'll move some purple over here, and we'll move some orange over here, so we have an equal amount of purple and orange dots on both sides. Our next type is called osmosis, and osmosis is the diffusion of water molecules through our permeable membrane, so through our membrane. And this is different because it's focusing just on the movement of water here. Nothing else is moving in our simulation. So let's take a look at what an example of that is. So if we take a look here, we have a high concentrated sugar and only a little bit of sugar here. So with osmosis, we're going to be moving the water over to create equilibrium. So if we look here, since there's more sugar molecules, there's less water on this side. So that means over here we have a high concentration of H2O, and here we have a low concentration of H2O. So what's going to happen with osmosis? We're going to move from high to low water concentration until we have equal water on this side and on this side. So the water level itself has changed, but we have equaled out the amount of water on this side to the amount of water on that side. So osmosis can be a little bit confusing with the solutes versus the water, because it might look like it's moving from high to low, or from low to high, I mean, but it's not the case. We're thinking of just the water molecules. So here again, we can see there are more water molecules, so we have a high concentration of water. So that's why it's moving over to where we have more solutes, because there's less water. There are three cases that this can be. The solution can be hypertonic, which causes the cell to shrivel. In plants, this is going to be called plasmolysis. In animal cells, we're going to call this creation. So one thing I do want to add to this definition of a hypertonic solution, here we're going to have our cells losing water. So that means there are more solutes outside the cell. And that's because if there's more solutes on the outside, the water is going to want to move so it can equal out how much water there is on the outside versus how much water there is on the inside of our cell. The next one is called an isotonic solution. In isotonic, there's the same on both sides. Equal, we'll see a little bit of movement, but it's going to stay in dynamic equilibrium. And then lastly, we have a hypotonic solution, and this causes our cell to swell. So plants become turgid, and that's called turgor pressure. And then animal cells will lyse or burst. So lyse means burst. So since the cell is swelling, we're going to know that there are more solutes inside the cell. The water is going to want to move in. So there's a couple ways that you can think about hypertonic versus hypotonic. Hypertonic, there's more solutes on the outside and the water is moving out. Hypotonic, our cell is going to swell. There's more solutes on the inside of the cell, so that means water is going to want to move into the cell to balance out and make that equilibrium. So this can be a really confusing concept, so please ask questions if you have it. But again, here's a visual representation. We can see our isotonic. We have the same amount of solutes on the outside as they're on the inside, so we're going to see just some movement of those back and forth of water. Hypertonic, we have quite more solutes on the outside. That means the water is going to want to move out to balance that solute out. And lastly, we have our hypotonic, nice big circle here, and we'll see more solutes on the inside, so water is going to want to go in to balance that solution. Our last type is called facilitated diffusion, and this is molecules like glucose, big molecules that cannot pass through the cell membrane's bilayer, so they have to use protein channels to get through instead. So again, it does not require any energy, but I want you to think of these protein channels like a straw in the membrane. So we have our membrane here. And our protein channel, again, is just going to be like that straw that allows the big molecules to pass through. So that's what facilitated diffusion is. There's no energy, so it's still moving with our high to low concentration, but we have something helping it, these protein channels. So that's why it is facilitated. So again, we can see still moving from high to low. We're going through our protein channel, which is our nice straw here, into the other side. So that's what we have for passive diffusion. If you have any questions, please reach out.